So let's continue our lecture on module 2 in the properties of mixtures in solutions and colloids. So in this lecture we're going to start with first about concentration definitions. So there are 5 types of concentration definitions that are commonly used. So the first one is molarity. Molarity is defined as the amount of solute by the volume of the solution. Molality is the amount of solute by the mass of the solvent. The only difference between molarity and molality is that we only consider the mass of the solvent in molality under the denominator. Parts by mass is mass of the solute by mass of the solution. Parts by volume is volume of the solute by volume of the solution. Mole fraction is the amount of solute of the mole. So amount of solute by the amount of solute plus solvent. So this is the definitions that we are going to use. So let's start with a simple problem first. So they're asking us to calculate the molality of a solution prepared by dissolving 32 grams of calcium CaCl2 in 271 grams of water. So remember that here they're asking us for molality. Now let's try and find this particular problem. First, let's define molality. So molality here is the amount of solute by the mass of solvent. So we can write N of the solute by the mass of the solvent. So N of solute here is CaCl2. So we are going to find, so they have given us the mass, which is 32 grams. So the number of moles is mass by molar mass. So how do you find this value here based on mass by molar mass? So mass here is given as 32 grams divided by, so the molar mass. So the molar mass of CaCl2 will be, so calculate the molar mass of calcium plus calculate the 2 times that of chlorine. So that value will be 110.98 gram per mole. So use the periodic table and calculate this value. So that becomes 110.98 gram per mole. So when you divide, you will get 0.288 moles of CaCl. So NCaCl2 is 0.288 mole. Now molality is denoted by smaller lowercase m, is given by N of solute is 0.288 mole divided by the total mass of the solvent is 271 grams. Remember that the mass of the solvent should always be in kilograms. So 271 grams in kilograms will be 0.271 kilograms. So that gives you a total value of 1.06 m CaCl2. So this is the molality of the solution in this problem here. So this is how you can calculate the molality. So pause the video right here and use the same principle and try to solve the following problems. Next, let's get into the next problem. So there are 3 problems here. So let's start with the first one. So they're asking us to find the concentration of calcium in ppm in a 3.50 gram pill that contains 40.5 milligrams of calcium. So the mass of calcium in the entire tablet is 40.5 milligrams. So the mass of the tablet here, so the mass of the tablet, total mass of the tablet is 3.50 grams. Now, how would you calculate ppm? So ppm, find the definition here. So ppm is parts by mass, parts per mass, parts per million. So that is mass of the solute by mass of the solution. Now, how would you calculate the ppm here? So parts by mass, parts per million or parts per mass percentage is given by the mass of solute by the mass of solution. So the mass of solution into 10 to the power 6. Remember that here it represents the parts per million. So ppm here represents parts per million. So parts per mass of the solute is 40.5 milligrams. So milligrams converted into grams divided by 3.50 times 10 to the power 6. So once you have this, that value becomes 1.16 times 10 to the power 4 ppm of calcium. So this is how you can solve the problem of ppm. So remember this formula for ppm: parts per million is mass of solute by mass of solution into 10 to the power 6. Next, let's go into the next problem. So here the label on a 0.750 liter bottle of Italian Chianti indicates that it's 11.5% alcohol by volume. How many liters of alcohol does the wine contain? So this is percentage by volume. So volume percentage, how would you calculate the volume percentage based on the problem that is given here? So first, let's try to find the actual definition. So that definition is volume percent. So volume percent is the volume of solute by the volume of solution. Remember, it's percent, so it's times 100. When it is per million, it's times 10 power 6, but when it is percent, it's times 100. Now here we want to find the volume of the solute, which is the alcohol. So volume of alcohol becomes, so push this side and push the 100 also this side. So it becomes volume percent times the volume of solution divided by 100. So volume percent is 11.5 and volume percent is 11.5 times 0.750 by 100. So when you calculate that, you will get a final answer of 0.0862 liter. So this is the amount of alcohol present in 0.750 liter of the total work here. Total amount of alcohol. Next, let's come to the next problem. So you have a sample of rubbing alcohol that contains 142 grams of isopropyl alcohol and 58 grams of water. What are the mole fractions of alcohol and water? So how would you calculate the mole fraction? So let's try to write down first the formula for mole fraction. So the formula for mole fraction is the number of moles of that particular one plus the number of moles of A plus number of moles of B. Now here we are finding first the isopropyl alcohol. So let's call A the isopropyl alcohol. So that will be equal to the number of moles of alcohol here will be equal to, so the number of mole fraction of alcohol is the number of moles of alcohol by the number of moles of alcohol plus the number of moles of water. So this is the idea behind the formula here. So this is how we generally look at the formula here. Now, the number of moles of alcohol here, how do you calculate the number of moles of alcohol? First, take in the grams here. So they have given 142 grams of isopropyl alcohol and 58 grams of water. So first, we have to find the number of moles of alcohol. So that becomes the mass of the alcohol by the molar mass of the alcohol. So the mass of alcohol is given as 142 grams. So 142 grams divided by, what is the molar mass of isopropyl alcohol? So the isopropyl alcohol given here is C3H7OH. So when you calculate the molar mass, that value will be equal to 60.09 grams per mole. So 60.09 grams per mole. So when you divide, that will be equal to, the number of moles of alcohol will be equal to 2.36 mole. Now number of moles of water, will be 58 grams of water divided by the molar mass of water is 18.02 grams per mole. So when you divide, you will get a value of 3.22 mole of H2O. First, we have to find the mole fraction of isopropyl alcohol. So my C3H7OH will be the number of moles of C3H7OH divided by the number of moles of C3H7OH plus the number of moles of H2. So that value is 2.36 mole divided by 2.36 plus 3.22. So that value will give you a final value of 0.423. Number of moles of H2O will be number of moles of H2O by number of moles of C3H7OH plus number of moles of H2O is equal to, so that gives you 3.22 by 2.36 plus 3.22 divided by 0.577. So this is how you can find the mole fraction. So use the same principles now. Pause the video right here and try to solve these problems. Next, let's try to discuss in how to interconvert concentration terms. So to convert a term based on the number of moles to one based on mass, we need the molar mass. And when you want to convert a term based on mass to one based on volume, we need the density. And finally, when you want to convert molality, molality involves the quantity of solvent, whereas the concentration terms involve the quantity of solution. So this is the only difference between molality and any other term. So molality only depends on the solvent, but the other concentration terms involve the quantity of the solution, whether it might be mass or volume. So let's try to use a problem and try to discuss this principle. So you have hydrogen peroxide is a powerful oxidizing agent used in concentrated solution in rocket fuels and in dilute solution as a hair bleach. So an aqueous solution of H2O2 is 30% by mass and has a density of 1.11 gram per ml. Notice that this is an aqueous solution, which means that the solvent here is water. So they have given us the mass percent and they are asking us first to calculate the molality. So how would you calculate the molality? So for molality, first thing we need to know is what is the amount of, so let's find the molality. Molality is the number of moles of solute by the mass of the solvent. So how would you find the number of moles of solute here? So notice that here they have given us that it's 30% by mass. So first, let's consider that there is 100 grams of solution. If there is 100 grams of solution, if this is 30% by mass, which means 30 grams is H2O2 and 70 grams is H2O, water. Because notice that it said that it's an aqueous solution. Now, how do you, so based on this assumption that it's 100 grams of solution, use the principle here to calculate the molality of this particular solvent. So how would you calculate the molality here? So first convert, we have to find the number of moles of solute. So it's the number of moles of H2O2 by the mass of H2O. So we have the denominator is 70 grams. So 70 grams converted into kilograms. So that value will become 0.07 kilograms. And number of moles of H2O2, so becomes the mass of H2O2 divided by the molar mass of H2O2. So the mass of H2O2 here is 30 grams divided by the molar mass of H2O2 is 34.02 grams per mole. So when you calculate this value, it becomes 0.882 mole of H2O2. So this becomes 0.882 mole. So calculating the value, you will get the final answer. So which will be 12.6 molar H2O2. So this is how you can interconvert from mass percentage into molality. Next one, they've asked us for mole fraction. How would you calculate the mole fraction here? So they've already given us the molality. So from this, we already considered that they have given us the mass percentage. But notice that mole fraction requires the number of moles of H2O2 by the total number of moles of H2O2 plus number of moles of H2O. So how would you find the number of moles of H2O2? It's already given here from the last one, so which is 0.882 divided by 0.882 plus we need the number of moles of H2O. That's about 70 grams. So 70 grams divided by the molar mass. So molar mass is 18.02 gram per mole. So that value will become 3.88 moles of H2O. So this becomes 3.88. So when you calculate it, you will get a final answer of 0.185. So the mole fraction of H2O2 is 0.185. So we have calculated the mole fraction. Next we have to finally calculate the molarity. So to find molarity, remember that in the principles that we talked about, when you want to convert a mass percentage, so when you want to convert mass here into volume, you need density. So they have given us the mass of the solution. So they've given us the mass of the total mass of the solution is 100 grams. So we want it into volume. We have to convert it into volume. So to convert this into volume, so we know that density D is mass by volume. So if you want to convert volume, we need mass by density. So what is the total mass of the solution? Total mass of the solution is 100 grams. In the problem, it's given that the density is 1.11 gram per ml. So 1.11 gram per ml. So 100 by 1.11 gives you 90.1 ml. So this is the volume of the solution is 90.1 ml. But for molarity, we need it in liters. So this becomes 0.0901 liter. So this is the final value that you have. Now, how do you calculate the molarity? Molarity uppercase M is the number of moles of solute by the volume of the solution. So the solute here, the number of moles of solute here is 0.882 mole. So 0.882 mole divided by the volume of the solution is 0.0901 liter. So when you calculate, the final answer will be 9.79 m H2O. So this is the molarity of the solution. So when you want to convert anything from mass to volume, so we already have the mass of the solution, but when you want to convert this mass, so when you want to convert this mass into volume, you need density. So remember this, if that value is not given, then don't consider doing that problem. So use the same principles now. Pause the video right here and try to solve these two problems. Next, let's discuss colligative properties of solutions. What are colligative properties? So colligative properties are the properties that depend on the number of solute particles and not their chemical identity. Remember that these are physical particles. Adding those physical particles changes the actual properties of the solution. So the number of particles in the solution can be predicted from the formula and the type of solute. Now, an electrolyte is simply, so let's start with the first one, is an electrolyte. So what is an electrolyte? Electrolyte basically is a solution that can separate ions when it dissolves in water. So when you have strong electrolytes, they completely dissociate, while weak electrolytes dissociate very little amount. And next one is a non-electrolyte. Non-electrolyte is a solution that does not dissociate to form ions. So here each mole of the dissolved compound yields one more of the particles in the solution. So let's talk about electrolytes. There are three types of electrolytes: strong electrolyte, weak electrolyte, and non-electrolyte. So electrolytic solutions are really good conductors, so which means that they can pass electricity through them. So a strong electrolyte passes 100%. A weak electrolyte passes partially, while a non-electrolyte is an insulator, while it does not pass anything through it. So next property is the lowering of vapor pressure. So the vapor pressure of a solution containing a non-volatile, non-electrolyte is always lower than the vapor pressure of the pure solvent. So that is generally given by the Raoult's law. Raoult's law basically states that the vapor pressure of a solvent above the solution is proportional to the mole fraction of the solvent that is present. So the vapor pressure of the solvent is proportional to the mole fraction of the solvent. So the vapor pressure of the solvent is the mole fraction times the original pressure of the solvent itself. So the pure vapor pressure of the pure solvent. So the vapor pressure lowering is basically proportional to the mole fraction of the solute present. So mole fraction of the solute present. So what is this? Why is this happening? Is because let's take a look at a pure solvent and a solution. So when you have a pure solvent, all of the particles in the solvent are the same. So the equilibrium is reached with the given number of particles in the vapor. But when you have non-volatile, non-electrolytic solutes, what happens is that these non-volatile solute particles are different in composition than the solvent. So the solvent particles are not able to vaporize as they need. So there is less amount of particles that can be vaporized because there is not enough collisions that are happening with the solvent molecules. So equilibrium is reached with fewer particles in the vapor. So let's try and solve a problem using the Raoult's law. So they're asking us to find the vapor pressure lowering delta P when 10 ml of glycerol is added to 500 ml at 50 degrees centigrade. At this temperature, so the vapor pressure of pure water is 92.5 torr and the density is 0.988 gram per ml, and the density of glycerol is given as 1.26 gram per ml. Now let's start with the first one. So when you want to calculate first, so let's look at the map of how you can calculate this. First, we need the mole fraction. First, use the volume of the glycerol that is present and multiply it with density. So when you multiply it with density, you get mass, and divided by the molar mass, you get the number of moles, and finally divided by the total number of moles, you get the mole fraction. So let's start with first finding the number of moles of, so the amount in moles of glycerol. So that is the mass by, volume into, so that is mass by molar mass. So but we do not know mass, but we know that density is mass by volume. So from this we can write mass as density times volume. So density times volume by molar mass. So the density of glycerol is 1.26 gram per ml. 1.26 gram per ml times what is the total volume of glycerol present. So when you have 10 ml of glycerol is being added, so 10 ml divided by the molar mass is 92.09 grams per mole. So glycerol is C3H8O3. So when you calculate it using the periodic table, you get this value. So the amount in moles of glycerol will be 0.137 mole of glycerol. So this is the number of moles of glycerol. Now we need to find the number of moles of H2O. So again, the number of moles of H2O is mass by molar mass. So mass we do not know. So density times volume by molar mass. So density of water is 0.988 times volume is 500 ml divided by the molar mass is 18.02 gram per ml, grams per mole. Now, so ml gone, so gram gone, we get final answer in mole. So that value becomes 27.4 moles of H2O. So this is the number of moles of H2O, this is the number of moles of glycerol. Now, how do you find the mole fraction of glycerol? So we don't need the mole fraction of anything else, we just need the mole fraction of glycerol. So is the number of moles of glycerol by the number of moles of glycerol plus the number of moles of water. So the number of moles of glycerol is 0.137 divided by 0.137 plus 27.4. So when you calculate it, you get 0.00498. Now vapor pressure lowering delta P is given as the mole fraction of glycerol times the vapor pressure of the pure solvent, so that is P of H2O. So that value becomes 0.00498 times 92.5 torr. So this is the value that's already given here. Notice that this is the value that we're using for pure water. So that value is 92.5 torr. So the final answer becomes 0.461 torr. So this is the lowering in vapor pressure when you add 10 ml of glycerol into 500 ml of water. So this is how much the vapor pressure will change or lower. So this is how you can solve the problem. So use the same principles now. Pause the video right here and try to solve these two problems. Next, let's discuss boiling point elevation. So a solution always boils at a higher temperature than the pure solvent. So this property is due to the vapor pressure lowering. Remember that as the vapor pressure lowers, the boiling point goes upward. So this boiling point elevation is proportional to the molality of the solution. So this change in temperature is given by Kb times m, where m is the molality, and Kb here is called as the molar boiling point elevation constant for the solvent. And these values are given by the table, so you can choose the table values from that. And the next one is freezing point depression. So a solution always freezes at a lower temperature than the pure solvent. So this freezing point temperature depression is also proportional to the molality of the solution. And we write delta Tf as Kf times m, where Kf is called as the molar freezing point depression constant for the solvent. And this is a table that shows you the values of Kb and Kf. So Kb and Kf. So these are the values that we generally take when we solve problems. So let's try and solve a problem here. So you add 1 kilogram of ethylene glycol antifreeze to 4450 grams of water in your car's radiator. What are the boiling and freezing points of the solution? So first we need to find the boiling point elevation and the freezing point depression. So we need to find delta Tb and delta Tf. So we know that in both the values we need the molality. So let's first find the molality. Molality is the number of moles of solute by the mass of the solvent. So let's take a look at this here. So you add 1 kg of ethylene glycol in 4.45 kilograms of water. So the mass of ethylene glycol, so ethylene glycol is C2H6O2, is given as 1 kilogram. So that's about 1000 grams. Now number of moles of C2H6O2 will be mass of C2H6O2. Sorry, let me write it as mass by molar mass. So how would you solve this now? So mass by molar mass is 1000 grams divided by the molar mass of ethylene glycol. If you calculate it, it will become 62.07 grams. So the number of moles becomes 16.1 moles of C2H6O2. So this is the value of m. Next, so now use this value and find the molality. Molality is the number of moles of solute, so which is 16.1 moles by the mass of the solvent. So the mass of the solvent is 4450 grams. We need it in kilograms, so it becomes 4.45 kilograms. So when you calculate the final answer, that gives you 3.62 molar. So molar C2H6O2. So this is the molality of the concept, molality value. So from this now, so let's find delta Tb first, which is Kb times m. Now we need to find Kb for water. So for water, the Kb value is 0.512 and Kf value is 1.86. So Kb value is 0.512 times the molality is given as 3.62. So that value will come 1.85 degrees centigrade. But they did not ask us delta Tb, but they asked us the temperature of the solution. So boiling point temperature of the solution becomes the boiling point of pure water plus the change in delta TB here. So the solvent here is water. So the boiling point of water is 100 degrees centigrade plus 1.85 degrees centigrade. So it becomes 101.85 degrees centigrade. So this is the temperature of the solution. So this is how much the boiling point will increase. Next, we need to find delta TF. So which is Kf times M. Kf is 1.86 from the table and molality is 3.62. So that value becomes 6.73 degrees centigrade. Now TF of the solution becomes TF of water plus delta TF. So TF of water, we know that it's 0 degrees centigrade, and remember this formula is minus, sorry. So it's a depression, so it's minus. Now this minus 6.73 degrees centigrade. So the final solution's freezing point is going to be minus 6.73 degrees centigrade. So by adding 1 kg of that ethylene glycol, so we are reducing the freezing point to minus 6.73 and we are elevating the boiling point to 101.85. So this is how you can calculate the values. So use the same principle now. Pause the video right here and try to solve this problem. Next, let's discuss osmotic pressure. So what is osmotic pressure? So before we discuss osmotic pressure, let's first discuss osmosis. So osmosis is a principle, or it's a phenomenon where the solvent particles will try to move from a higher concentration region to a lower concentration region through a semi-permeable membrane. Remember that solvent will always flow from a more dilute solution to a more concentrated one. Now, osmotic pressure is basically the pressure that must be applied to prevent the net flow of that solvent. So again, remember this, osmotic pressure is basically the pressure that you need to oppose that motion of osmosis. So that is given by pi equals mRT, where m is the molarity, r is the gas constant, universal gas constant, and T is the Kelvin temperature. So let's take a look at osmosis here. So one side we have pure solvent, the other side we have solution. So solvent will always move from a higher concentration region to a lower concentration region. So here there is high concentration of solvent. Here there is low concentration of solvent. So the solvent particles will try to have a net movement towards the solution. Now you notice that there is a change in pressure that is caused because more particles are entering inward than there are going outward. So what will happen is that one side there will be an elevation in the pressure. To oppose that, we apply an osmotic pressure. When you apply that osmotic pressure, what will happen again? There is net movement outward, outside, than the rate inward. So keeping that pressure in will prevent the solvent from flowing to the other side. This is the idea behind osmotic pressure. So let's take a look at a problem and let's try to solve this problem. So they have given us what is given here. So biochemists have discovered that there are 400 mutant varieties of hemoglobin, the blood protein that carries oxygen. So a physician dissolves 21.5 milligrams of one variety in water to make 1.50 ml of solution at 5 degrees centigrade. She measures an osmotic pressure of 3.61 torr. What is the molar mass of the protein? So let's try and solve this problem here. So what is given first? Write down first what is given in the data. So the osmotic pressure is given as 3.61 torr. Next, they have the temperature, which is given as 5 degrees centigrade. So we know that pressure should be in atmosphere. So convert this into atmosphere. So 3.61 by 716. So that gives you a value. So 3.61 by 716. That's in atmosphere. And temperature 5 degrees centigrade. So convert it into Kelvin. So it becomes plus 273.15. So that gives you 278.15 Kelvin. So we have the pressure and the temperature. And they have given us, they're saying that you have the molarity. So they're asking us to calculate the molar mass of the protein. So to find the molar mass of the protein, we need the molarity first. So we know that from the osmotic pressure formula, pi equals mRT. So from this we know that m becomes pi by RT. Pi is 3.61 by 760 divided by R is 0.0821. Remember that R is in the atmosphere values, plus, so times 278.15. So that final value will become 2.08 times 10 to the power negative 4 m. So this is the molarity. So we know that molarity is mass by volume. So from this, let's calculate the number of moles. So number of moles is molarity times volume. So molarity is 2.08 times 10 to the power negative 4 divided. So that is the times the volume will be the total amount of physician is dissolved 21.5 milligrams in water to make 1.50 ml of the solution. So that is the solution. So 1.05 times 10 to the power negative 3 liters. So that gives you a value of 3.12 times 10 to the power negative 7 mole. So this is the number of moles of that particular solution. Now from this we have the molar mass. So molar mass depends on, first let's calculate the molar mass here. So what is the molar mass? How do you calculate the molar mass? So we know that number of moles is molar mass, so mass by molar mass. So molar mass becomes mass by the number of moles. So mass, how many grams has it dissolved? 21.5 milligrams. Convert it into grams. 21.5 into 10 power negative 3 divided by the number of moles is, we have calculated is 3.12 times 10 to the power negative 7. So the molar mass becomes 6.89 times 10 to the power 4 gram per mole. So this is the molar mass of the protein hemoglobin from the problem what is given. So this is how we can calculate the molar mass of the protein. So it's about 68,900 grams per mole. So that's how large the protein is. So use the same principle now. Pause the video right here and try to solve this problem. Next, let's discuss volatile non-electrolytic solutions. So for a volatile non-electrolyte, so the vapor of the solution contains both solute and solvent. So the presence of each volatile component basically lowers the vapor pressure of the other, since one lowers the mole fraction of the other. So for such a solution, the vapor will have a higher mole fraction of the more volatile component. So this vapor has a different composition than the solution. So this is generally given by the strong electrolytic solutions first. So a strong electrolyte solution always dissociates completely to form ions, and each mole of solute gives 1 mole of dissolved particles. Now the formula for the compound indicates the expected number of particles. For example, in NaCl, you have two ions, so there are 2 moles of dissolved ions. So when you dissolve 1 mole of NaCl, you have 2 different ions here. So which means that when they dissociate, you get 2 moles of dissolved ions. So one factor that is used to predict the effect of a solution is the Vanov factor. So Vanov factor takes into account the dissociation of the strong electrolyte to predict the effect of the solution. So that value is denoted by I. I is the measured value of electrolyte solution by the expected value of the non-electrolyte solution. So the same formulas take into place for electrolytes, but we add the constant I, the Vanov factor, into every one of those formulas. So this I value is generally determined by the table by the ions in the solution. For example, when you take FeCl3, the expected value of the total number of ions is 4, but the observed value is only 3.4. This way, there might be a differentiation, but there might be cases where the values are the same as well. So Vanov factor changes based on the solute that is used. Now, let's take this example here. So you have a 0.952 gram sample of magnesium chloride dissolves in 100 grams of water in a flask. Which scene depicts the solution the best? So let's take MgCl2 first. So magnesium chloride is MgCl2. So when it dissociates, you get Mg2 plus and Cl minus. So there is one for every magnesium. There should be 2 chlorines. So which scene depicts them the best? So let's take a look at this here. So the blue one is MgCl2 and the green one is magnesium chlorine. So for every 1 magnesium there should be 2 chlorine. So in the first one you notice that there are 1, 2, 3, 4 magnesium. 1, 2, 3, 4, 5, 6, 7, 8. So A is the answer. Next, what is the amount represented by each green sphere? So first we need to know, based on the grams here, first convert the grams into the number of moles. So number of moles of MgCl2 becomes mass by molar mass. So let's calculate the mass first. So mass here is already given, so which is 0.952 grams by the molar mass here is 95.21 gram per mole. So that value becomes 0.0100 mole of MgCl2. Now, if MgCl2 is 0.01, notice that for each 1 MgCl2, you get 1 Mg2 plus ion and 2 Cl minus ions. So there is one of these and there's 2 of these. So which means if this is 0.01 mole, then this becomes 0.01 mole. This is 2 times that value. So which means it becomes 0.02 mole. So each green sphere, there are total of how many magnesium are, so this is the total number of moles of magnesium, sorry, chlorine is 0.02 mole. So for each green sphere, how many are there? So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 of them. So each green sphere represents how many moles? 0.02 mole by 8. So that value becomes 2.50 times 10 to the power negative 3 mole. So each green sphere represents 2.50 times 10 to the power negative 3 mole. Next, finally, they are asking us, assuming the solution is real, what is the freezing point at 1 atmosphere? So how would you calculate the freezing point? For that, we need the molality first. So molality M is given as the number of moles of solute by the mass of solvent. So the number of moles of solute here is given as 0.01 mole of MgCl2 divided by the mass of the solvent is, the total is dissolved in 100 grams of water. So 100 grams converted into kilograms, it becomes 0.1 gram. So that gives you a value of 0.10 molar, so molar MgCl2. So based on the expected value of I for MgCl2 here, we can consider that if you have an ideal solution, so notice that here, assuming the solution is ideal. So when it is ideal, it means that the I value is ideal. So MgCl2 contains a total of 3 ions, 1 plus 2. So I becomes 3. So delta, they are asking us to calculate the freezing point. So delta TF is I times Kf into M. So I is 3 times Kf here for MgCl2 would be 1 point. So Kf here for water, what is that in water? So for water is 1.86 times M is 0.1. So that value gives you a value of 0.558 degrees centigrade. Now, what is the temperature of the solution? Freezing point of the solution is going to be delta TF plus TF of water. Sorry, this is going to be TF of water minus delta TF. So TF of water is 0 minus 0.558 degrees centigrade. So the final answer will be minus 0.558 degrees centigrade. So this is the TF of the solution. So that is how you can calculate the freezing point of the solution. So use the same principle now. Pause the video right here and try to solve these two problems. So one of the best uses of vapors and best uses of the solution properties is fractional distillation. So where you heat up crude oil vapor and you pass it with steam, and each vapor condenses at different temperatures. So the one with the higher temperatures condenses first. As it goes upper and upper, so the one with lower and lower temperatures condenses, finally giving out gas. So next example of this is blood. So blood maintains what we call an isotonic. Osmotic pressure is required for your blood cells to be in shape. So the cell shape is determined by the osmotic pressure. If the internal pressure is not equal to the external pressure, the internal liquid intracellular fluid pressure is not equal to the extracellular fluid pressure, then you end up getting distortions in your cell shape. So if the pressure is uniform through inside and outside, we call that an isotonic solution. If there is lower concentration of particles in the cell than the cell, a hypotonic solution is the one that has a lower concentration of particles than the cell. So this is called as a hypotonic solution. Hypotonic solution will always absorb water and swell until it bursts at some point. The second one is a hypertonic solution. Hypertonic solution is where it has a higher concentration of dissolved particles than the cell. So if the cell is placed in a hypertonic solution, water moves out of the cell and causes it to strain. So this is another factor that can be determined in another disease, which is generally called anemia. So it happens to the cell shape in the same manner as well. Next, finally, let's go to colloids. So colloids are mixtures which are heterogeneous mixtures. So for example, let's take aerosol. Aerosol is liquid dispersed in a gas. So an example of this is fog. If you have aerosol dispersed, so when you have a solid dispersed in a gas, we call it smoke. When you have a gas dispersed in a liquid, that is whipped cream, so which is generally foam. So solid foam is gas dispersed in a solid. So example of that is marshmallow. When you have an emulsion, emulsion is paint. So when you have liquid, so that is milk. Solid emulsion is liquid dispersed in a solid, that is butter. So sol is solid liquids dispersed in a liquid, so that's paint or cell fluid. And solid sol is solid dispersed in a solid, generally opal. So this is the idea behind the colloids. So colloids exhibit one another effect called the Tyndall effect. So let's compare light passing through a solution and a colloid. So when light passes through a solution, it does not show any light rays. It generally passes through because it's transparent. But when you pass it through a colloid, it disperses. This dispersion effect is generally called as the Tyndall effect. So when you see sunlight that is scattered by dust in air, this is another example of the Tyndall effect, where you would see this phenomenon happen. So with that, we end our lecture on the properties of mixtures, solutions, and colloids. I'll see you again in the next lecture.